Okay, thanks. These are the contents I was discussing. So coming to the first slide, that is types of aero engines. So in this we are going to see there are two major types of the engines, that are air breathing engines and non-air breathing engines. Already you know that. So in non-air breathing engines, if you see the rockets, so without any air or the support of the atmosphere, they are going to work in the space. So that air or whatever the combustion products are required, that are carried in the air rocket itself. So that type of engines we are calling it as non-air breathing engines. And coming to the air breathing engines, so in the mechanical syllabus, many times you have studied that reciprocating engines and jet propulsion engines. The PPT is visible to all the participants. And reciprocating engines, we have many times we have discussed about the two-stroke engines, three-stroke engines, or the cylinder engines, or the different types of fuel engines like that. And now this topic is about the jet propulsion engines. So in that we have, other than the on-road vehicles, we have also jet propulsion engines or the turbojet engines. So in that we have gas turbine engine, which is our main focus today. Then we have pulse jet engine, ramjet engine, and the scramjet engine. So depending upon the Mach number, we are going to distribute these engines. So we'll discuss what is the Mach number and how these engines are differentiated. And before that, we'll discuss the working. So coming to the working, here you can observe the jet engine. So first one is the jet engine, where you can observe at the inlet from the left side, the air is going to come inside. And these engines, majority of the times, will have a compressor stage. Then we have combustion chamber, and then we have the turbine stage. So these are the three main components or the three main chambers which is required for all the gas engines. So now air will enter the compressor stage through the diffuser. Air will be compressed at very high pressure, which is required for the combustion. And in the combustion, we are going to supply the fuel, which is required for the increasing the temperature as well as the thrust from the engine. So these all aero engines will work on the thrust produced by the engines. So that thrust we are going to get by combustion products. So that hot gases of the combustion products will be coming out from the gas turbine stage. And because of that thrust in the fluid or in the atmosphere, that thrust, because of the thrust, it is going to move in the further direction. So similarly, we have ramjet engine. So in the ramjet engine, there are no moving parts. This is very important. So in the ramjet and scramjet, if you see the design, we don't have any moving parts at all. We have only the chambers in three stages. So in the ramjet, you can observe it is just similar to the gas turbine engine. Like a jet engine, we have compressor stage with a diffuser, then combustion chamber and the nozzle at the exit. So if you see the diffuser side, we have the two types of diffusers. That is, one is supersonic diffuser at the inlet side. One is the subsonic diffuser at the combustion side. Because when the scramjet, if you talk, or the ramjet, if you talk, the Mach number or the speed of the engine is very high. So at that high speed, the air should be inletted to the combustion chamber at very high pressure and at the limited speed, like nearly between the subsonic speed. So for that, we have supersonic as well as subsonic diffuser that is going to compress the air and it is inletted to the combustion chamber. Then in the combustion chamber, as you know, the fuel is supplied at a given rate as per the required thrust or the power, and this is going to combust and it is going to produce the major thrust. Now last, coming to the scramjet engine, here we may be having only the compressor stage where we have the diffuser type of the model. So for that, we have only the diffuser where it is going to convert that supersonic speed of air nearly to the subsonic, because it's not possible to always to compress up to the subsonic speed. So nearly to the subsonic, it is going to be compressed, or if it is very high speed, we can call it as a supersonic combustion, where the speed of air is very high. So in such cases, we don't need any working materials or the moving materials in the engine. So this engine is going to have only the chambers without any moving parts. So at that speed, if the combustion is going to take place at supersonic speed, that we are going to call it as scramjet engines. Now coming to the other side, rocket engine you already know, which is going to have the air tanks as well as fuel tanks inside the engine itself, and at a given time both are mixed and burnt outside, so that rocket can work in any atmosphere, or without atmosphere also it can work in space. So that example I have taken. Below you can see the pulse jet engine. This is a special type of gas engine where there is no turbine, and here you can see the number of valves are connected, which are closing and opening at a given time, like our Otto cycle engine, where the fuel is inletted and closed with a valve in internal combustion engine. So with that engine, we are going to supply the fuel, and once the fuel is supplied, the valves of the air are going to be closed. That is the difference. So air valves are closed. So once the chamber is completely closed on one side, other side, which is calling it as tailpipe or the exhaust nozzle, the thrust is going to be produced because of the combustion gases which are going outside the tailpipe or the nozzle. So like this, it is going to work in the pulse jet engine. If you see the applications, majority of the applications are there in the gas turbine engines or the jet engines, because those are all working in the atmosphere at very low altitudes, and these scramjet or the ramjet still under research, and many applications we cannot see, or if they are there, like ramjet engines, these are working in the stages. Okay, and coming to the pulse jet, it is going to produce in steps. So one by one, the amount of fuel and air is mixed in a one given cycle. It is going to burn, and again a fresh fuel and air is going to mix. Valve is closed, and again it is going to give the exhaust. So it is going to sound like your bullet vehicle. So like that sound will be coming. So for a low weight or the very light vehicles, you can go for pulse jet or the other type of engines. Coming to the next slide. So this slide I have included So in this slide, one can understand what is the Mach number. So at the bottom line, you can see Mach number is written. So this Mach number is nothing but the ratio of vehicle or the aircraft engine with respect to the speed of sound. So speed of sound, if you talk, it is the speed of sound in air, around 330 meters per second. You might have studied somewhere. So with respect to that, if you take the ratio, we are going to get some number. If the vehicle speed is same to the speed of sound, then we can call it as Mach number 1. So because the ratio is 1. So like that, the Mach number is written to the bottom side. On the y-axis, if you see, it is the specific impulse. So specific impulse is nothing but the thrust produced by the engine in newtons or kg to the weight of the fuel burnt per second. So ultimately, we are going to keep the units in same standards, and the result we are going to get in seconds. So impulse force is written on y-axis in seconds. So according to these two xy axis, if you see, the turbojet engines and the rocket engines, only those two engines are operating from the 0 to maximum Mach number. Or if you see the turbojet engines, it is going to operate from the 0 in the sense it is from the land. It can take off, it can start from the land, it can operate up to some speed, and it can come back to the land. So that if you see, it is having some Mach number up to 3 or 3.5. Now from 3 to 6, if you see, ramjet engine is going to work, because the moving materials are very less, but the chambers are almost similar to the gas turbine, and the diffuser is only having the supersonic diffuser, so that we have the very low speed between 3 to 6. That is called as ramjet engine. Still, if you go for higher speeds of the engine movement with very low changes in the diffusion or something else, or in the supersonic combustion, if you tell, that comes under scramjet engine. So scramjet engine will work under above some 6.5 or 7 Mach number to up to 10 or 12. So up to that Mach number it can work. And finally, if you see the rockets, it can start from 0 or the land, and it can go in the any space or any atmospheres. That is a very speciality of the rockets. But keeping in mind the impulse or the specific impulse, if you see, the efficiency is very less, because specific impulse is very near to the 0. In the sense, the thrust produced per weight of the fuel taken is very less. So because we are burning more amount of fuel, So the thrust produced will be very less for the rockets, or the specific
So,
what you are taking, that will be very less. So comparatively, we are going for the more efficient engines, more specific impulse, or we need more thrust for a small amount of fuel burnt. So for that, we are going for the turbojets in the maximum applications. And at the top, you can see there are two fuels we are comparing in this graph. That is hydrocarbon, as usual we are using. But still, if you go for the hydrogen fuel, the Mach number is going to remain same, but the impulse force or the specific impulse, we are getting more. So that is a big advantage of going for the other fuels like hydrogen fuel and other things. Next, we are going to take the working stages. Just a minute. So in the working stages, if you see, one of the aeroplane or the turbojet engines at the bottom figure is the PPT visible? Is the presentation visible? Just chat here. Okay. Now it is visible. So some participants are not getting the PPT. Okay. So here if you see, one of the normal commercial aeroplane is taking one of the engine which is connected at the top. So here we have two-stage working or the three-stage working also in the rocket engines. If you see, we are working in stages because, as I told, ramjet engine and scramjet engines cannot work from the land or they cannot take off directly. So for that, these commercial vehicles like aircraft working with the turbojet engine, and in the bottom figure you can also see a turbojet engine assisted one setup is there or the launcher is there, and above that one scramjet engine or the ramjet is connected. So once it reaches the high speed, say for example up to some 4 Mach number or the 5 Mach number, then these scramjet or the ramjet engine combustion will be started. Automatically they can take off from the given positions. And later to stop them or land them is a very difficulty. So in such cases what they will do is, for these ramjet or scramjet engines, maximum time they will go for the missiles application for the bombing or the missiles and any other crashing requirements. So in such cases, once they run the scramjet or ramjet engines at this Mach numbers, they will take for the only crashing applications. Next is types of the gas turbine engines. So as I told you, there are different types of engines. Coming to that, the gas turbine engines or the turbojet engines have the more applications. So in that we are going to focus more in this presentation. So these 4 types major I have shown in the different diagrams so that understanding will be more. So turbojet engine, if you see, we have the gas turbine with the afterburner. We can take it example later. So that jet engine you can observe how it is working. That is called as turbojet engine. One more side, turbo propeller you can see. So turbo propeller you can observe a turbojet engine connected with a propeller or that fan like element which is going to propel the engine in the forward direction. That type of vehicles we are going to call it as having turbo propeller engines. At the bottom side if you come, there is normal commercial vehicles. If you have seen aircraft engines, maximum times the passenger vehicles are connected to with such type of engines. So that is turbo fan engine, which is having a turbojet engine at the back side, plus a fan is connected, a big fan is connected at the front side. So that fan is required for cooling purpose or the air conditioning of the aircraft or any other applications where the air requirement is more. So in such cases, we are going for turbofan engines. Next is turbo shaft engine. This is very, very important because in many applications or industrial applications where the shaft work is required to run the generators, to generate the power, or to run the helicopter propeller at the top. So in such cases, we need this turbo shaft engine. The shaft is directly connected to the fan so that the lift can be taken from the helicopter, or the shaft can be directly connected to a generator so that it can generate the power. So like this, we have the different types of gas turbine engines. Next slide we'll take. So is the presentation speed is okay for everyone? Am I going fast or is it okay? Okay, thank you. So now we'll come to the working, how it is different from the gas turbine applications. So here we'll see the first one, turbojet engine at the top. So here you can clearly observe first two stages will be having some compression stages. Then we have high compression stages. So this will be acting like a diffuser. So from the nose at the inlet side, the air is going to become inside. So that air will be increasing the pressure with the help of compressor. Then that high pressure air is taken in the combustion chamber. And in the combustion chamber, it is completely annular. So you can feel the complete 360-degree form of the engine. In that, we have combustors like 12 combustors in the annular position, or it may be 8. Number of combustors can be connected in the annular position, so that in the tailpipe, the complete thrust should be produced in the equal thrust or equal power. So that we have the annular type of combustors. The combustors are connected in 360 degrees. And next you can see there are turbine stages. Actually speaking, these turbine stages will not help us to give more thrust or more power to the engine. These turbines only required to run the compressor stage. Okay. Or in industrial applications, as I told you, in the power applications or the helicopter's engine, if you see, there we need the turbines because these turbines are connected to a shaft. There we need to generate some power from the shaft. But actually speaking, for the jet engines, we don't want these turbines to actually run. But to run the compressor, we need some stages. So number of compressor stages, if you compare to the turbine stage, the turbine stages are very less. So that is one intention. So there are different sections they have shown, hot section, cold section, like that. So our today's focus is more on hot section. Next engine, what you can see is at the bottom side is a turbofan engine. Now speaking to the very light or less passenger. So I request the participants to keep the audio off so that disturbance will be less. So turbofan engine, if you see, a fan is connected at the front and a small gas turbine engine or the turbojet engine is connected at the back side. So it is similar to the same jet engine. But speaking about the turbofan engine, these fans are required to propel that vehicle. Main intention is a very light vehicle if you take, or very light aircraft like 4 passengers or very light cargo vehicles if you see, we need only propulsion at very low speed or whatever, and people don't want to enjoy the trip also. They want more time to enjoy in that cases, or they don't want any in very less time they are in emergency or something. So in such engines, if you see, we want very slow engines at very low speed movement. In such cases, we can go for the turbofan engine, which can propel the engine only by the fans, and very small thrust is produced by the gas turbine engine or the jet engine at the backside. So this jet engine is required only for the running the fan, not for the giving more thrust. So thrust is not important here. Only the propeller speed is important. So that propeller speed sometimes may be connected to the gear box, and the speed can be reduced or increased depending upon our the requirement. So this is one of the turbofan application or the engine working. Next PPT, if you see, this is the turbo propeller. This is having maximum applications in the commercial vehicles or commercial aircrafts. So here also you can see a turbojet engine at the backside. Again here, shaft is very important. That shaft movement is taken with the gearbox, and with the gearbox help, they are connected to the turbo propeller. Just a minute. So this propeller, again, as like fan also, here again a gearbox is connected and the propeller speed can be maintained. Here also the speed of the propeller, it is going to propel the vehicle at a given speed. And in the fan engine, you may get confusion now. Why the fan is important, why the propeller is important. Fan is required to generate more airflow on the engine so that cooling is possible, or extra air can be taken in the vehicle chambers for the air conditioning purpose or any other purpose. So later that we'll talk about the bypassing this air from the fan engines. And also the propeller, if you see, The propellers are used to propel the engine in the forward direction. As I told, the engine is very less importance here. We need more importance to the propeller, where it is going to propel the engine at very low speeds, not compared to the thrust speed or whatever. So thrust engine will be very small and propeller will be very big. So according to the required speed, they are going to run this propeller. Next, turbo shaft engine, if you see, here again, the shaft is connected from the turbine or compressor. So as the turbine gets the energy from the combustible gases, the turbine is going to run in a given direction, and the torque is generated from the shaft. So this shaft, by using the bevel gears or some other gear arrangements, we can connect to the fan of the helicopter or the rotating blades of the helicopter. And in this engine, the forward direction or the backward direction or lifting and lowering or turning actions are all controlled by the tilting of these blades. So these blades are having some mechanism where the tilting of complete blade arrangement, or else the single blades can be tilted in around the 360 degrees. It can be tilted in any directions. So to control the lifting and turning movements. Same engine is also used for power generating also, because same shaft can be connected to the generator. It can generate the power also. So like this, we have various applications depending upon the engine use. Next, you can see in which all altitudes these turbines can work. Okay, so here at the left side, I have shown the height of the or the altitude of the ground from the ground. So that is from 4 kilometers to up to around 12 kilometers. So if you see the up to what position we have the atmosphere, so majority of the times in the poles you have up to 9 kilometers we have atmosphere, and the equator, up to equator if you come, in that side atmosphere is up to around 12 kilometers or 16 kilometers also. So depends upon the air density and the movement. So until that range, these all aircrafts can work. So you can see here a small aircraft with a turbo propeller engine can work up to 9,000 or 9 kilometers from the ground. That is one thing. Helicopters can work up to 6 kilometers. Then a commercial airlines and the turbojet engines can work up to 13 kilometers from the ground, up to the maximum limit of the atmosphere. And above this, if you go, then we need for the rocket engines, where we need to take the atmospheric air or the combustible products which are required. So one is the oxygen and one is the combustion fuel. So both you have to carry and you have to go there. But here for the all these aero engines, the carrying capacity will be less, the load carrying capacity will be less. So keeping in that mind, so whatever fuel is required, that will be carried, and remaining oxygen can be taken from the atmosphere what is available. So as you go from the ground to the top level, the density of air and temperature will be reducing continuously. So in such cases, what we have to do is the speed of the engine should be increased, because for more thrust we need more mass flow rate of the air, so that more fuel can be inducted, more fuel combustion can be possible, more thrust can be possible. In such cases, that's why from the land to top level if you go, we need to go on increasing the fuel inlet. Am I audible to everyone? Okay. So next slide, I have taken industrial gas turbine engines. So this all already discussed. We'll see once again. So applications like land, where power generation we are using like simple or combined different gases, or the combined cycles like steam turbines can be run by the gases. By burning the gas in the gas turbine engine, you can get the steam. That steam can be used for the running for the steam turbines. So like that we can generate the power. Next is the vehicles. So many times you might have seen the jugars outside. The jet engines or the pulse jet engines are connected to the vehicles on road, and some racing competitions will be done. So on roads also they are using locomotives or the tankers. So armed tankers are also using these gas turbines, because many times it cannot be dependent only on the engines or the internal combustion engines. So anytime if the requirements is there, they can go for the jet engines also. Next is, as I am telling, industrial gas turbine, we are talking about the shaft engines or the gas turbine with a shaft. So that is also used for the helicopters. Then coming to the sea also, there also we can use for the ships. So earlier ships were using the diesel engines where maintenance is more and space utilized for the different components of diesel engine was very huge. So nowadays, if you see the gas turbine engine, if it is replaced with a gas turbine engine with a shaft and a propeller, it can use very low space. Maintenance is also very less. Moving parts are also very less. So that's why they can go for the ships also. And next is the submarines. Now question comes in the submarines, as anyhow it is working under the water, how it is going to combust the fuel. So here what happens is, in submarine, they will be having different tanks for the fuels and oxygen, both, or the air. So whenever the submarine comes to the top surface of the sea, there they are going to absorb all the air and they are going to store in the tanks. So both air as well as fuel is stored in the tanks, and whenever they go inside the water, they will burn the fuel and run the submarines. Next is the petroleum platforms. It is just for running the compressor, like radial or the centrifugal compressor can be run so that gases and petroleum products can be pumped to the other locations. So here you can just observe the fuels used in the engines. So fuels used here, majority of the cases we are going to use the kerosene as a fuel or gasoline and various alcohols. And many times to differentiate from the regular kerosene or the regular or petrol fuel, they are going to give some codings like Jet A, Jet B or jet propulsion fuels. So these codings are given just to differentiate from the given density, and main requirement is it should not explode for a higher temperatures. So it can return with the higher temperatures as well as the cold temperatures, because as and when the aeroplanes are moving at the higher altitudes, the temperature is very less. So in such case also it has to work with a proper flow. Also we have propane, butane, and many times they call it as MAP gas also, that is methyl acetylene, propyne and propane. So such gases will be also used. So storing the gas is very difficult, but they will go for the liquid fuels most of the times. And also coming to the biofuels, how these biofuels are also helpful. So nowadays you might have heard the biofuels in the gas turbine engine is also utilized in different percentage of blendings. So the gasoline engines or the kerosene engines, they are going to have some blendings. So the fuels like Jatropha, algae is there. From the algae, the fuels is extracted. Camelin is there. Then different vegetable oils or cooked, used cooked oils. From that, they are going to extract the fuels, and those are mixed with the aircraft engines. But here, anyhow, the efficiency is going to be reduced and thrust is also less. But just to have the commercial applications like very low, lightweight aircrafts, they can go for the alternate fuels like biofuels also. And at the bottom, I have written that India is also tested the aircraft with Jatropha fuel with the blending up to 50%. That flight is taken place in between Dehradun and Delhi in 2018. So this will give us one opportunity in this field where the biodiesel is also having very much requirement in the Indian field, Indian side also. So India is also trying to prepare such biodiesels in the future. Now next is the gas turbine engine with afterburner. So here you can observe a gas turbine engine at the top, which is having again 3 stages. So here you can see compressor, there are 2 stages, and also the turbines are also 2 stages, and both are connected with the different shafts. Such things we can call it as multi-spool engines. So spool in the sense the hollow shaft. So one shaft will rotate inside the other shaft, so that first stage of compressor will take the rotation of the last stage of the turbines, which are at very low speed. Then at the first stage of the turbine, after the combustion at very high speed, which is running the second stage of the compressors. So here we have different 2 spools, and later also we can connect these spools with the requirement for the power generation and other things, or else we can use it for the aircraft engines. At the bottom you can see this same engine is connected with the afterburner. This is what is the importance nowadays. What is that is, whenever you run the engine with only one combustion chambers, the thrust is constant and the speed of the engines or the the lifting of the engines or the takeoff is also at a constant speed it is taking place. But once you go for the afterburner, so afterburner is nothing but we are going to introduce extra fuel at the end of the turbine stage, and this extra fuel is going to generate maximum thrust or sudden thrust you can call. So whenever the takeoff is required or the whenever speed of the engine should be changed, in such cases we can go for the afterburner applications. So you can observe at the top graph, you can observe the takeoff with afterburner, without afterburner, how it is going to differentiate, and also to take place in military applications some changing of the direction suddenly or changing of the speed suddenly, so that opposite people cannot understand the movement of the aircraft. Then their applications we need the afterburner, so which is going to help the military people. Next PPT is on the parts. So here you can understand one turbojet engine is kept there. So from the right side, if you see from the image, from the right side, it is having a air inlet, a compressor stage, combustion chamber. Then we have turbine stages and a long pipe at the left side. What you can see is the tailpipe for the afterburner. So before that afterburner, many connections are there for the fuel supply. And the last part of that engine, if you see the left side, it is a nozzle. So nozzle will going to control the amount of fuel or the exhaust gases to be taken outside. So that nozzle is going to operate for the changing the speeds. And below you can see on the right side below picture, that is showing the compressor blades with the stators. So in between you can see the stators which are fixed there at the on the casing of the engine, and the compressor blades are connected on the drum or the disc of the compressor which are rotating. So these stators are going to help the direction of the airflow to compress the air. Rotors are going to be compressing the air continuously in the stages with reduction in the area. So that will help us to increase the pressure. Next is the combustion chamber, where we have the combustion chamber with some perforations. You can see number of holes are produced, so that anywhere or the casing of the combustion chamber, if you see, there are two liners or the two casing. Inside casing is going to have the direct contact with the combustible gases. Outside chamber is going to have the contact with the cold air or the air which is coming from the compressor. So once the cold air is going to be moving inside with the perforations, the fuel is going to come in contact and it is going to have the combustion. So similarly here also in the turbines, if you see next slide, so right side sketch you can see, or the picture you can see, the turbine stators are connected in between, which are not rotating, which are just directing the gases in a given direction so that turbine blades can run. Then we have the rotor blades and stators. So between this we have the cooling passages. So this we'll discuss in the later PPT. And also you can see the assembly, how these rotors and stators are connected. So the stators, you can see it is split into two halves. So on this casing, all the stator blades are connected with the required number of blades. And the compressor rotor, if you see, or the turbine rotor also, if you see, on the disc which is rotating, which is connected to the compressor rotors, that turbine blades are also connected on the disc and which are going to be rotating at the high speeds. So this is like a assembly, what you can understand. In the next slide, so in this slide you can see the turbine. After the turbine we have the afterburner stage. So these pipelines, what you can observe, it is coming from the fuel tanks. So with the nozzle and the pipeline, we are going to connect these fuels to the afterburner. So afterburner is nothing but a fuel holder. So that a strut, on that strut or the V gutters we can call that V passages, V like passages. So in that fuel is inserted. So combustible gases which are coming outside and which is mixed with the cold air or the compressed air, fresh air we can call. So some part of the fresh air, some part of the combustible gases. So already burnt gases are going to mix with the fresh air Also the extra fuel is supplied. So due to this, what happens, sudden thrust is again developed whenever it is required to increase the speed of the engine, or sudden change of the directions if required. We can inject more fuel to burn this in the afterburner. So this is the figure which is in color. You can observe the afterburner parts. So where the fuel supply is there, and cold air for cooling the casings, that is shown in the blue color. So that air is also taken for combustive burning this extra fuel. And later you can see the nozzle, which is the changing with the given area. So that mechanism is also connected there with the sleeves. So next, coming to the working principle of these gas turbines. So already many students have studied this in your books, that is, which is working on the Brayton cycle. In this Brayton cycle, if you see the graph below here, so it is going to work on the Brayton cycle with two isentropic processes and two heat addition and heat rejection processes. So if you want to increase the thrust, what you can do is you can increase the work. So work done by engine, if you want to increase, one has to increase the pressure as well as the temperature. So whenever you go for the higher temperatures, there is a very difficulty of maintaining the temperature of the blades, which should not melt at the given temperatures, because these gas turbine engines are working at very high temperatures, so which may affect the melting of the gas turbines or the stators or the casing of the combustion. So this should be taken care. So for that only we have to go for the cooling thing. Also, if you only increase the pressure suddenly, like say for example P1 to P2, if you increase the pressure without changing the much of the temperature, so in that case what will happen is only the pressure is increasing, not the temperature. So that will what will happen is only the thermal efficiency can be increased, not the thrust or the work done. So to keep both in mind, to increase the thrust as well as efficiency, what you have to do is you have to increase both pressure ratios as well as the temperature ratios. So keeping this equation in mind, that is 1 minus 1 by Rp raised to gamma minus 1 by gamma is nothing but what? That is depends on the pressure ratio. And the isentropic process, the pressure ratios can be related to the temperature like this. That is P3 by P4 if you take raised to gamma minus 1 by gamma. You can also write it as T3 by T4. Why I am concentrating on T3? Because this is the major temperature which is going to affect the complete thrust and the efficiency of the engine. So this T3, if I supply in the main equation, that is the thermal efficiency of Brayton cycle, 1 minus T4 by T3. So as the T3 increases, what will happen? The complete equation or the value of that 1 minus T4 by T3 is going to increase. So to increase this thing, we have to always increase the inlet temperature of the turbine stage gases. So this will help us to increase the efficiency of the engines. Now the question comes, if I go for the engine without cooling, if I go on increasing the temperature, what may happen? So here what will happen, as the turbine blades are rotating at very high speeds with high temperatures and very high centrifugal forces also, the thermal stresses, the higher temperature which may cross the melting point of the blades, because metals, if you see, we have up to around 1100 degrees centigrade as a melting point for the alloys. And even if you go for the super alloys or some nickel chromium alloys, we have the higher temperatures, so which can sustain up to around 1900 or 1700 degrees centigrade with cooling. So here cooling, how it will be done, that we'll see later. So to overcome this heating problems with the gas turbine blades from the failures, we need the materials which can limit up to the higher level of melting points and also with the cooling. So various materials you can just observe here. Just a minute. Is it audible now for everyone? PPT is visible? Okay. So here coming to the outer body of the turbojet engines, covering of the engines or the complete body of the aircraft, if you see, Nowadays, maximum times the composite materials are used, more than 50% with the metals. So they are nothing but the carbon fiber or the glass fiber materials they can go for. Then compressors, we need high strength or the high energy materials. So they are nothing but the steel or titanium alloys or silicon carbide materials. Then cobalt nickel based alloys. So like this you can go for the different materials. So even in a compressor you may feel that it is a very cold condition or a cold stage. In that also, after compression of the last stage, if you see, the temperature is around from 300 to 500 degrees centigrade, which is not less. Still it is a high temperature, but compared to the combustion chamber and the turbine blades, this is very low temperature. So we are calling it as a cold condition. But still after long run of the engine, this compressor stage is also coming to overheated. So for that also we are going to use the same alloys. Then the combustion chamber, you can see we have the superalloys nickel. This nickel chromium is very important for the high temperature applications, where it can withstand the high temperatures and long run of the engines. So for that we can go for the superalloys or the nickel chromium alloys. Next is the very hot chambers like turbine and the afterburners. So here we can go for the carbon fiber blades which are coated with the ceramics, or you can go for the alloys with the nickel chromium, and also we can go for the ceramic coating. So this ceramic coating is very important. So in the maintenance stages, what they will do is they will again and again they will go for the ceramic coating so that the blade life can be increased. And also the important is, before making these turbine blades, the cooling procedure in the casting process itself should be maintained properly. So it should be unidirectional cooling should be taken place in casting, as well as the material should be single crystalline, or whatever the grain size or the grain distribution is maintained, it should be very smooth and fine, and it should be uniform throughout the blade length. So that should be maintained. Next is the coating. After that we have the pneumonic and Inconel alloys that also can help with the coatings. Then next we have casing material. So this should be a simple aluminum alloy or the steel alloy with high strength and heat treated metals that you can use. The next is the challenge. So now cooling can be done by various methods. One method is either taking directly the compressed air as a coolant, or you can carry the liquids or the evaporating liquids in the engines. This will be very difficult, right? Because whenever you carry something else in the aircraft, it's very difficult to also attach with the cargo or the passenger. And carrying these all liquids and other material, which will add some more load on the engine, so that thrust will be very less. So in such cases, until today, we are going to have only the air coolant method, or cooling with the air only. So here main intention to go for cooling, first is we should not compromise on the thrust, we should not compromise on the efficiency, and also the life of the engine and the blades. So later I will show the blade how they are, the profile. You can see how much difficulty is there to manufacture such type of blades. So in these conditions, the designer should aware of all these things, and whenever you go for cooling, the temperature of the inlet turbine stage is also going to reduce. But what we are going to keep in mind is the thrust is going to increase. So when the thrust is required more, so blade cooling and the cold temperature of the turbine inlet stage or the turbine surface temperature, that we are not bothering, but we are bothering on the more on the thrust. So if the thrust is bothered more, then combustion chamber and the gas turbine blade cooling also, we can generate the more thrust with the high temperature, because that high temperature gases are not directly coming in contact with the turbine blades. So next, if you see the cooling methods, so as I told earlier, because of the high temperatures in military applications, if you see with afterburner, it is around 1800 degree centigrade or up to 1900 degrees centigrade. The cooling is very important. So coolings are various types. In internal cooling, we can go for internal impingement cooling, ribbed passages, so passages with increased surface area, that is called as ribbed passages, or passages with the pin fins. So pin fins also increase the surface area, which can absorb more heat. Then we have external cooling like film cooling, or the exit slots of the turbine blades. So this last point you can just observe here, the bypass ratio. This is very important. So whenever you go for the compressor air, the compressor air is divided into three parts. One part will be going to the blade side, major for combustion. One part will be going for the cooling of the casing. Another part will be taken for the cooling of the shaft and discs. So like this, three stages are divided. So that division of the compressor air is called as bypass, bypassing the air. So around 20 to 40% of air is diverted only for the cooling purpose or for the air conditioning of the aircraft vehicle. So this is called as a bypass ratio. Or that air moving from the compressor is also called as bleed air. So here you can observe the nozzle guide vane cooling passages. It's very important. This is the stator. So before combustible gases are inletted towards the turbine or the rotor blades, there we are going to supply the gases in a given direction to hit the moving blades. So that is called as a stator or the nozzle guide vane. This is going to act as a nozzle, which is a reaction turbine here. So this stator is going to come into first step where the high temperature of gas is going to impinge on the nozzle guide vane. So you can observe these nozzle guide vanes can be connected to the casing on one side, and it is having two passages, one at the top and one at the bottom, and also it is having two edges. One is the trailing edge at the back side, another is the leading edge. So leading edge is the front side of the nozzle where number of holes you can see from the start to end. So these are holes are the alternate holes, one on the side the other it is drilled, and beside we have one more trailing edge. Inside that what is that is called as inserts. So these, with the help of inserts and the surface of the blades, the air which is coming from the inside passages at a very high pressure from compressor is going to prepare the impingement cooling. So that is shown here. So again we will discuss in the next slides. So this is the gas turbine blade which is connected on the disc, and it is going to rotate at very high speed. And left side sketch you can see the hot gases in red color are coming and hitting the blades after the nozzle guide vane. So this is hitting at the first leading edge. So on the leading edge we need more cooling for the impingement cooling and other applications. And at the back side if you see the trailing edge, the slots are prepared. So number of slots are prepared or the ducts are prepared. That will help us to the cooling of the entire blade length in the where more shocks are prepared by the gases. And on the right side of the blade, if you see the section or the cut section of the blade, that in the top you can see the passages, and in that passages, the bottom side sketch if you see, the turbine rotor is connected to the disc, and air can be possible to be taken from the disc only, not from the casing, because it is not connected to casing. So air is going to be passed from the bottom of the or the root of the blade, and in these two passages they have shown there are different designs. This is one of the design. In this you can see the ribbed passages. The passages are made with the ribbed and pin fins or impingement holes or ducts like that. So due to the high pressure, so this cooling air is going to be passed through these passages, and it is going to come out from the blade tip or the side of the blades, suction side, pressure side. So like this it is going to be keep the blade material in the cold condition. So here I have shown the fluid passage. So directly you can see the fluid passage inside the blade. So from the root the coolant is coming, air, and it is going through the ribbed passages coming out of the impingement holes or the side holes, and also the exhaust side. If you see the ducts are there or the slots are there through which it is going to the outside. So left side is the suction side and the other side is the pressure side. Pressure side is nothing but from the nozzle guide vane, the gases are coming and hitting the plates. So where the high pressure is there, that is the pressure side. Suction side is where the gases are just passing over the other side of the blade. So here, as I told you, there are three passages from the compressor. So one you can see that is for the combustion, air is taken. Second one you can see the air is taken for the nozzle guide vane or the stator's cooling. Also the blade tip and the casing, there you can go for the cooling. Bottom side third part, if you see the compressed air is taken through the disc of the compressors or the below the combustion chamber. There are number of holes on the disc and connectors. So those perforated passages will give the air through the disc, and this disc of the turbine will be having some number of holes. The entire disc itself is hollow, and through that passages will be made, and the passages are connected to the turbine blade also while connecting. So through this the blade cooling is possible, and the air is going to be taken away after the exhaust. Here you can see how the film cooling is done. So earlier you have seen with the inserts we are going to have the impingement cooling. Pin fins are connected for the increasing the surface area and ducts which are internal or the ribs passages. But here if you see, once the impingement holes are supplying the cold air from the inside, those air movement is going to prepare some film on the surface, and this film is going to try to mix with the hot air or not mixing with the hot air, whatever. But this cold air is going to prepare some thin film or the cold surface on the blades. So this will help us to maintain the turbine temperature at the lower conditions. So here, for example, I have taken one CFD analysis where only fluid part of the air or the coolant is modeled here with different holes, pin fins and impingement holes. So this part is taken only at the center part of the blades, because always if you see the blades at the center part is having the more pressure, more temperature which is acting on the blades. So only the trailing edge we have taken just to show the how in CFD we can understand the flow is taking place or not, mixing is going to be taking place or not properly, or maximum amount of air is going to be taking place or not. And in the leading edge you can clearly now here you can see the dimples. Those dimples are helping the insert to be kept in a given position. So that dimple is earlier shown here in the nozzle guide vane. Just extended circular surfaces on this insert. You can see that the bottom dimples is written. So that dimples are used just to connect the insert and fix it in a given position. So those are shown here. Next we'll come to the how this CFD will help us. So in this I am trying to show you pressure. So on the suction side, on the other side of the blade where the pressure of gases are very less, as the pressure is very less, more coolant is taken out. So that's why on the suction side many times the number of holes should be very less. So more coolant is not required there, but the temperature of air is very high. Still we need some limited number of coolant passages. But in the pressure side, if you see, more number of exhaust pipes with the or exhaust holes with the coolant is required, because you can see that by the color itself it is indicating high temperatures on the suction side. At the exit slots you can see the blue color, which is nothing but the cold condition, means their cooling is properly taking place, but major importance is what? Leading edge side. There you have to focus more. Next again example, same examples I have taken on the side views, pressure side and suction side. So here in the velocity vectors you can see the direction of air, how it is moving outside. So like this you can use CFD tool with different blades, different models, different pressurized flows, different passages of flows, and one can understand, because when the engine is running one cannot understand whether it is working properly or not. But by CFD analysis or some other analysis one can understand the flow, how it is going to take place, whether the coolant is properly working in the turbine blades or not, because whatever the cost is implemented here, the taking place with the manufacturing of these blades is very huge. So we should not lose that blades easily, or the failure of the blade should not be done. So for that you have to check the cooling passages like this. So one can see the impingement holes, how they are hitting on the outside surface and cooling is taking place. So this is all about the presentation. So now I request the students to take some assignment questions like, my main intention was to find your find the industries near your areas which are working on these aero engines or gas turbine blades, so that you can take some internships or projects. Also, you can check the manufacturing process in this blade cooling or the blade manufacturing things. Also, one can find out some more applications of the gas turbines other than this what I have explained in the PPT. So this is my first trial. I have tried to cover the basics of the gas turbine engines types and blade cooling. So later we can take the other lectures on the similar lines. Thank you. So any questions? If I can answer, I will try. You can unmute the mic. So another 5 minutes, I'll share the feedback link. WhatsApp. Just message. Copy. Paste. So in the feedback link I have shared in the chat, so all of you can fill it and get the certificate. Any questions? The feedback link is available.